Okay, welcome to Introduction to Structures. This is problem 4. This is reactions, shear forces, and bending moments for a simple supported beam. In this presentation, we are going to study the analysis of reactions and internal forces for a simple supported beam, but it's a particular simple supported beam, because as you see in the screen, there is an overhanging on both sides of the beam. So this will produce a difference in the usual distribution of the bending moments and shear forces. So this is a simple supported beam, but in the two extremes, as I mentioned, there is an overhanging that will act actually as a cantilever beam in this side and this side of the structure. So the other thing that is different, if you compare this exercise with the previous ones, is that this exercise is a little bit more complex in terms of loads. So this overhanging simple supported beam is subjected to two UDLs. One of them is 6 kN per meter, the second one is 12 kN per meter. It's subjected as well to punctual loads in different positions, and is subjected as well to concentrated moments. One is 15 kN per meter at this left extreme of the structure, and another is at 2 meters of the pin support and is 24 kN per meter. So this is certainly the most complex structure we will study at this stage. So in the first place, what we need to do as usual is to establish the free body diagram of the beam, showing clearly what are the expectations in terms of reactions. Because this simple supported beam does not have any horizontal loads applied, we don't expect to have any horizontal reaction in the pin support at the point A. This is the reason why in these free body diagrams, the only reaction that appear are VA at the point A, which is the vertical reaction at the pin supports, and VB, which is the vertical reaction at the roller. So once we have the free body diagram, we can start writing equations of equilibrium to establish the values of the reactions in the first place. So the first analysis we are going to do in order to be sure that the horizontal reaction is equal to 0 is to write the equation of summation of forces in the horizontal direction. And evidently, even if we add an horizontal reaction H at the point A, where we have the pin support, this will be the only force in the horizontal direction and will need to be equal to 0 to keep the equilibrium in the horizontal direction. This is the reason why mathematically we can demonstrate that this reaction will be equal to 0. In order to establish the value of the vertical reaction VB at the roller, we are going to write the equation of summation of moments around the point A. So at this point, we can see that if we compare this with previous exercises, we have forces and moment to the left, and we have forces and moment to the right. When we are calculating reactions, we need to take into account the whole structure, and not only the left side or the right side of the structure as we do when we establish the shear forces or the bending moments. So the summation of moments around the point A for this structure will be then minus 15 kN per meter, which is the punctual moments applied in the left extreme of the structure, minus 18 kN, which is the equivalent load of this UDL, which is equal to, if I remember well, let me just check. So the first UDL is 6 kN per meter, the second is 12. So the equivalent load for the first one is 18 because it's 6 times 3, and the equivalent load for the second one is 12 times 2, which is equal to 24. And this is what we have in our free body diagram. So the summation of moments around the point A then is minus 15, the anti-clockwise punctual moment applied in here, minus 18 times 1.5, negative because it's anti-clockwise as well, plus 24 kN per meter, this punctual concentrated moment applied at this position, plus 24 sorry, 24 is the concentrated moment, plus 24 times 4, which is the moment of this equivalent load of the second UDL, multiplied by 4 meters, the distance to A, plus 60 kilonewton times 6, because 6 meters is the distance from 60 kilonewtons to the point A, and it's positive because it's clockwise, plus 12 kilonewtons multiplied by 9, the distance from 12 kilonewton to A. We have 2 and 2 is 4, 5, 6, 7, 8, and 9 meters, as you see. And it's positive because it's clockwise, and minus the moment produced by VB, which is the reaction at the roller, multiplied by 7 meters, the perpendicular distance to the point A. And all of this, the summation of the whole set of moments on this structure, has to be equal to 0. So rearranging this equation, we can calculate, we can establish the value of VB, which is the reaction at the roller, as I said, equal to 78 kilonewtons at the point B. In order to establish the reaction VA, which is the vertical reaction at the pin supports to the left of this beam, we are now at B. So the first moment we have is minus 15, which is a concentrated moment in kilonewton per meter, minus 18 multiplied by the distance, which is 8.5 meters, plus 24, because this is a positive moment, concentrated, kilonewton per meters, minus 24 multiplied by 3 meters, negative because it's anticlockwise, minus 60 times 1, because it's anticlockwise as well, plus 12 multiplied by 2, the perpendicular distance to the point B, and plus the unknown VA multiplied by 7 meters, which is the distance from VA to the point B, and all of this has to be equal to 0. Rearranging this equation, we find that the reaction at the point A, where we have the pin support, is 36 kilonewtons. Putting all together, this results in terms of reactions. We have the free body diagram with all the reaction already calculated. We have only 2 vertical reactions, the first one at A, 36 kilonewtons, and the second one at B, 78 kilonewtons, with all the other forces applied on the structure. So now we are ready to start the determination of the shear forces and to sketch the shear force diagram. In this occasion, I'm not going to use equations. I'm going to construct, or I'm going to sketch directly the shear force diagram, looking at the structure directly and explaining how to do it when you already understand exactly what is this concept. So we are going to construct, or we're going to sketch the shear force diagram. We are going to consider that A is our origin of coordinates. So Z is the horizontal axis, as you see here, and Y is the vertical axis. So this is the center of coordinates of this coordinate we have established. So in the first place, I'm going to focus my attention in this cross section in blue, just before the reaction VA. And as you see, we need to start analyzing the left side of the structure or the right side of the structure with the opposite sign, because we are doing the shear forces. And to the left side of the structure of this cross section, what you see is the only force that is producing shear forces is 18 kilonewton, which is the equivalent load of this 6 kilonewton per meter, this UDL you can see here. The moments do not affect at all to the shear force diagram, because they are moments. So the only forces that affect the shear force diagrams are the vertical forces. So at this cross section in particular, then, we have a negative force giving us a negative shear force equal to 18. So we can draw from our neutral axis, our reference line, horizontal reference line, this value that will represent 18 minus 18 kilonewton, which is the shear force at this cross section in blue. Because we know that there is an UDL, and we know that the variation of the shear force is linear under UDLs, and because we know as well that at this start point of the structure, the shear force is equal to 0, because if you check to the left side of the structure, there is nothing producing shear forces, we can establish the variation from 0 to minus 18 after the analysis of the shear force at this cross-section in blue. So this is the first part of the shear force. After that, if we move our analysis to the cross-section exactly after the reaction, we realize that the shear force at this cross-section is equal to minus 18 plus 36, which is equal to 18. So after the point A, after the pin support, what we are going to have is a shear force diagram equal to 18, which is again 18 minus 18 plus 36. So this shear force becomes positive after the pin support. After that, if we move along this interval from A to, let's say, 3, we are going to see that what we have is a constant shear force equal to 18 kilonewtons. So we are going to use this horizontal line to represent this constant distribution of the shear force. After that, we are going to move and we're going to see what happened at this new cross-section in blue at the end of the second UDL. And if we check, what we have in there is basically minus 18 minus 24 plus 36. And the result of this operation is minus 6. And minus 6 is the shear force at this cross-section in particular. And because we have an UDL and we know that the distribution will be linear, we can connect these 2 points and we have this part of the shear force diagram for this beam. After this cross-section, in the interval from the blue cross-section to the new force 60 kilonewton applied to the structure, the distribution of the shear force will be constant, as you know. And after that, immediately after, because we have this force, we are going to have an additional shear force negative coming down, so we can add this 60 to this diagram, and in total we're going to have minus 66, because this is minus 60 minus 6 is equal to minus 66, will be the value of the shear force at this cross-section. After that, the distribution from 60 kilonewton to B will be constant again, because we are between forces, and from that point we need to add the reaction 78 kilonewtons, and this is what we are going to do now. So 78 positive minus 66 is equal to 12. And 12 is the force, the last force we have in this structure that will close the diagram and will end this sketching of the shear force diagram, basically. So after this construction, we can see that we have the shear force diagram complete for the structure. We have certain intervals where the shear force is positive and equal to 18, for example, in here, and in here is positive as well, is equal to 12, and we have the maximum negative shear force in this area where we reach minus 66 kilonewtons. So now we have the shear force diagram. We are able to go and to start analyzing the bending moment diagram as well. And this is what we are going to do now. So in this case, as I mentioned, because it's an overhanging structure, we are going to have negative bending moments, as you will see in a moment. So what we're going to do is we're going to start the analysis cross-section by cross-section again, as we did with the shear forces. In the first place, just after the point of application of minus 15 kilonewton per meter, you see that you have a concentrated moment that this will be reflected in the bending moment diagram as a value, negative value on top of the reference line, equal to minus 15, because this is a concentrated moment applied at that particular cross-section. After that, we move to the point A, where we have the pin support, and we do the summation of moment to the left side of the structure. What we have is basically minus 15, the concentrated moments, minus 18 times 1.5, the distance from this equivalent load to the point A, where we are calculating the bending moment. And the bending moment in total will be minus 42 kilonewton per meter. So we can sketch this value in certain scale. This will be minus 42. And because we have a UDL, and we know that the distribution of moment under UDL is parabolic, we can connect with the parabolic function these 2 points, and we have the distribution of the moment in the first interval from this extreme to the point A. The next cross-section we are going to analyze is the cross-section that is immediately before the point of application of 24 kilonewton per meter, this concentrated moment. So we are at the blue cross-section, and in there the moment will be equal to minus 15, the concentrated moment applied in here, minus 18 times 3.5, the distance from this equivalent load to the point of the cross-section in blue, plus 36, the reaction multiplied by 2 meters, the distance to the cross-section in blue we are using for the analysis at the moment. So the result of this calculation is giving us minus 6 kilonewton per meter. So we can sketch in certain scale on top of the reference line because it's a negative moment. And because we are between loads, we know that the distribution of the bending moment is linear. So then we are going to add this line in here to represent the distribution of the moment in this second interval in our analysis. If we go now to the cross-section exactly after the concentrated moment of 24 kilonewton per meter, we have to add to our equation of moments this 24. So basically, the moment at this new cross-section in blue is minus 15, minus 18 times 3.5 because it's anti-clockwise, plus 36 times 2, the moment produced by the reaction, and plus 24 because 24 is a positive moment and because it's clockwise. Doing the operation, we have 18 kilonewton per meter. We can sketch at the bottom of the reference line because it's a positive moment, and we can continue the analysis to the next cross-section. The next cross-section to be analyzed is the beginning of the second UDL. We are in this blue cross-section at the moment. So at this particular point, we call M 3 meters because we are 3 meters from A. The moment is minus 15, minus 18 times 4.5, the distance from 18 to the cross-section in blue, plus 36 times 3, which is the moment of the reaction, and plus 24. This is equal to 36. So we can sketch 36 again, and we can connect these 2 points with a linear, with a line, because we know that between forces the distribution of the moments are linear. And we can go now to the next cross-section, the cross-section at the end of the second UDL. At this cross-section, you have in here the equation that gives you the value of the moments, and the result is 48 kilonewton per meter. So it's basically minus 15, minus 18 times 6.5, the distance from 18 to the new blue cross-section, plus 36 times 5, the reaction times the distance to the blue cross-section, plus 24 and minus 24, because it's 24 times 1, the negative moment produced by the UDL to the left side of the structure. So we sketched it in here already, the bending moment diagram for this interval. The next cross-section is the cross-section at this blue line in here, as you can see in the screen. And in this case, to simplify our calculation, we're going to use the right side of the structure to calculate the moments. So in this equation, I will start with minus because I'm going to use the right side of the structure. I will open a bracket, and what we have is, to the right is 78 times 1 meter, negative because it's anti-clockwise, plus 12 times 3 meters, the moment produced by 12 kilonewton to the right side of the structure around this cross-section in blue. And the result is 42 kilonewton per meter that is sketched in here. And again, the distribution between these two forces will be linear because this is what happened in terms of bending moment diagrams when you are between forces. The next cross-section to be analyzed is the cross-section B, where we have the roller, and we are going to do the calculation to the right side of the structure because it's simpler. So I start with minus and open bracket, and I have only 12 kilonewtons times 2, which is 24 kilonewtons per meter, but it's negative because it's a negative moment. And we can sketch it in this way as a vertical line on top of the reference line because it's negative. We can connect these 2 points with a line, and we can connect again these 2 points with a line because from between 78 kilonewton and 12 kilonewton, we are between forces, and the distribution of the moment will be linear. And of course, the moment at the end of this beam is equal to 0 because there is no any force or any moment applied that will produce any value of moment different to 0. So with this, we have completed the bending moment diagram for this particular beam. So now we are going to do the analysis of these results together. So at the end of this analysis, what we have is the shear force diagram and the bending moment diagram for this beam, and we have the reactions all expressed in the engineering language in here. So the thing is that many times we are interested in the localization and the value of the maximum moment. And as you know, the maximum moment is where the shear forces are equal to 0, because the relation that exists between the functions that are representing the distribution of the moment and the functions that represent the shear forces distribution. So as you know, the shear forces are functions that are derivative from the bending moments, and this is the reason why where you have 0 shear forces, you will have maximum bending moments. This 0 in here is in aligned with this local maximum in here, minus 42 for the bending moment. This 0 in here is related with this local maximum in here, and this 0 in here is related with this maximum local for the bending moment in here. Of all the maximum moments in the bending moment diagram, there is a global maximum, which is this one in here we are going to establish. And in the first place, in order to calculate the moment, we need to know the location of this 0 in the shear force diagram. In order to establish the location of this 0 in this shear force diagram, we need to play with these triangles in here. We have two triangles. We have a triangle of a height in blue of 24 kilonewtons, and the base is 2 meters. And we have another triangle, which is an equivalent triangle because they share all the angles. And we have x, which is the distance we need to calculate, and we have the height of 18 kilonewtons. So doing the relation between triangles, as you can see here, x is x over 2 is this base over this base is equal to the relation between the height of the small triangle over the height of the big triangle. So with this relationship, we can rearrange and we can calculate x, which is twice 18 divided by 24, which is 1.5 meters. So now we know that x is equal to 1.5 meters. So basically we have the location of this point, and we can start, or we can write the value, or the equation that gives us the value of the maximum moment. In order to do that, we're going to use the right side of the structure. So I put in here the equation of maximum moment is equal to minus, I open the bracket because I will use the right side of the structure. So we are here at 1.5, or in the middle of this 1 meter, you can see here. So what we have is the moment produced by this portion of the UDL, which is 12 times 0.5 times 0.25, plus 60 kilonewtons times 1.5 meters, positive moment of this 60 kilonewton, plus 12 times 4.5, which is 12 multiplied by the distance to the position of the 0 in the shear force diagram, and minus 78, the reaction multiplied by 2.5 meters, the distance from this cross section in here to the 78 kilonewton, which is the reaction of the roller, basically. So doing the operations and closing this bracket, of course, we get the maximum bending moment for this structure, which is 49.5 kilonewton per meter. So as you see, independently of the complexity of the structure, the procedures are exactly the same. The only problem you can face in this type of exercise is the amounts of information you have to manage, and you need to keep attention, and you need to try not to make mistakes when you do the calculations of forces and distances and so on. So this is all for this exercise then. So thank you very much for watching, and in the future we are going to offer more videos like this to analyze more and more complex structures.